Okay, I'm going to move on to the second part of information theory. So we've looked at one aspect of transmitting information, namely the aspect of how do we encode what is being sent in a desirable way. The second aspect concerns what happens if there is interference, if there is noise that might corrupt the message being sent. What are the ways in which we can deal with that? So as a general heading for this issue, we have how do we keep the noise down? Nice quote from a very famous German philosopher, Arthur Schopenhauer. I have long held the opinion that the amount of noise that anyone can bear, undisturbed, stands in inverse proportion to his mental capacity, and therefore be regarded as a pretty fair measure of it. So what we are concerned with is what happens in what are referred to as channels. So we've considered one aspect already, what happens when a message is prepared for transmission, and the processes of transforming symbols into binary characters. The mechanisms involved when the message is received and decoded into what has actually been sent, those are effectively reverse process, very similar to the actions involved in sending. What we're going to look at in this section is what affects the middle of that activity. So messages are sent through what we call a channel. Now a channel is just a generic name for something like a copper wire, what the physicists used to refer to as the ether, an optical cable, a mobile network frequency. It's just a general medium through which messages are sent. And there are a few questions that arise. One of these is how can the sender of the message be confident that the message has actually arrived uncorrupted? How can the person to whom the message has been sent actually be confident that what they've received is what was intended to be sent? So noisy channels can have some quite disturbing behavior. So here are a couple of well-known famous examples of garbled messages. Send 3 and 4 pence, we're going to a dance. This is a failed telephone message that was sent to the British Army headquarters during the First World War. One I remember from my time at primary school. It used to be the case that when kids were taking on outings, field trips, it would be necessary to hire a minibus. And so one would have conversations such as the coach hire company might ask, how many people do you need buses for? And I went to school in Scotland, and on one famous occasion, the teacher responsible for organising the trip replied, oh, about 67. What was actually intended but the message is deciphered as I had on the previous slide. So the British Army field telephone message that was sent was actually not send 3 and 4 pence, we're going to a dance. It was send reinforcements, we're going to advance. The coach hire case, the number of buses asked for wasn't sufficient for about 67. It was about 6 to 7. That is between 6 and 7 people, not as it became transcribed in Scots, 67. So we have this, just as we did with communication, an abstract model of channel behavior. We have a source of the message. The message is you, which takes up m bits. And this is going to be encoded as an item to be sent through the channel. It'll be encoded in n bits as x. So X goes in one end of the channel, which may be affected by noise, and Y, another message containing N bits, comes out at the other end. That message is decrypted into Z, which again contains M bits, and that is the message that goes to the intended receiver, the destination. So what we have, we encode U with M bits as a message X that contains N bits. So we have this conventional notation. The encoding of U is X. And that's what goes into the channel. If noise is present in the channel, what will emerge at the other end is a binary sequence Y, and this might be different from what was sent through the channel. So Y is decoded. We use again this notation, decoding a Y, and Y is decoded to a message Z. And Z, which is M bits long, is what is seen by the receiver. And what we're trying to minimize is the possibility of errors. So we encode in N bits messages that only need M bits. Ideally, we want the number of bits we are using in encoding to be relatively small compared to the original message size. So we don't want unnecessarily to pad out the message that is being sent. We don't want too much redundancy. We can think of noise in a channel as being the probability that errors are present, that errors are going to arise. So the abstraction we're using, we are thinking of the action of the channel as the message passes through it. It takes encodings of an input word and it produces an output word which is going to be decoded. So we have 4 parts. The original message X, the encoding of that message that goes into the channel, that is U. The message that actually comes out at the other end, Y, and the final message itself, when everything is decoded, is Z. Now, given the way noise behaves, we can't predict with absolute certainty what is going to appear as the communication Y when X is given as input. When we're sitting in a train compartment, we cannot tell exactly how long it will be for the person screaming into their mobile phone to bray at the top of their voice, "I'm on the train!" So, we're encoding in binary. So we're going to use a particular class of what we call as noisy, or what we regard as noisy channels. And the source symbols we have are zeros and ones. So a sequence of symbols, U, is going to be translated into a binary sequence X, sent through the channel and appear at the other end as Y, and Y is going to be decoded to give the message as Z. In an ideal world, Z and U are going to be exactly the same. So let's suppose we have probability values, P, which is between 0 and 1, and Q, which is strictly less than a half. And these probability values, these are modeling the situation in which the probability of an input symbol being 0 is equal to P. The probability that that symbol is a 1 is equal to 1 minus P. We only have two symbols in our alphabet. So that is basically just saying the input is going to be a 0 with P and it's going to be a 1 with probability 1 minus P. Now, the other probability, Q, that is capturing the phenomenon of an error, of noise occurring. So, when an input bit X is left unchanged, that is going to happen in this model with probability 1 minus Q. But with probability Q, the input bit is going to be flipped. So a 0 will become a 1 with probability Q. A 1 will become a 0 with probability Q. This is why we have the restriction that the probability of a bit being flipped is less than a half. So, what's going to happen when we send in bits? With the model we've described, if we don't make any changes at all to the message we are sending, in other words, if we don't use any encoding scheme but just send the message unchanged, then with that model, standard probability analysis, roughly Q multiplied by M bits are going to be corrupted. So what that means is if the probability of a bit being flipped is quite large, if it's very close to a half, the message that we actually receive, it's not going to be likely to look like the message that was sent. So the probability of error, in other words, that the message we send you is not the same as the decoding of the encoding of that message, that probability is going to be quite high. So how do we get around that problem? And what we do is we build some redundancy in. So let's look at an alternative method. We take our starting message and then encoding it, we repeat the individual symbols in the message 3 times. So in other words, if our message is just a single 0, we encode the message that's going to be sent as 3 zeros. If our message is 011, we encode the message to be sent as 3 zeros followed by 3 ones followed by 3 ones. And to decode, what do? We find the ith bit of the decoded message just as the symbol that occurs most often between the sequence y sub 3i up to y sub 3i plus 2. So here's an example. If the message we are going to send is 3 zeros followed by 3 1s followed by 3 1s, so that's what goes into the channel. And the message we get after it's been passed through the channel is not exactly the same. It's 0 1 0 1 0 1 1 1 0. Then when we decode that using our majority approach, what we find is the decoded message is 0 1 1, the message that was originally intended to be sent. Now, this technique of trying to reduce the probability of errors, this is called repetition coding. So in that approach, we reduce the chance of the text being corrupted by repeating its content and applying a majority vote rule to the result. So in the previous situation, where we don't make any changes at all, and we have one bit at a time transmission, the probability of an error occurring is Q, because that's the probability that a bit is going to be flipped during transmission through the channel. When we repeat each bit 3 times, what happens? The probability of an error is only going to occur if at least 2 of the 3 bits are corrupted. So in other words, if 0, which we encode as 0, 0, 0, actually arrives as 0, 1, 1, or 1, 0, 1, or 1, 1, 0, or 1, 1, 1. And the probability of that occurring is this calculation there. And that, when we do the algebra, is strictly less than Q. So we cut the probability of error arising, but at a cost. We reduce the bit rate. So before, when we didn't make any changes, we had the probability of error of Q, but an optimal bit rate. When we make changes, this repetition coding scheme, we reduce the probability of error, but we are sending 3 bits for every single bit of the original message. So the transmission rate, that depends on the encode-decode convention we're using. So in the example I just described, we're using this repetition coding. In general, we have what is called a scheme, a method for encoding and a method for decoding. The transmission speed is called the scheme rate. That's denoted by R. That's the number of bits that are sent each time. So messages with M bits are padded to messages with N bits, and the rate of transmission is M divided by N. So let me just summarize what I've been talking about in classical information theory. It was very introductory discussion. What we looked at is encoding schemes, the problem of what's called source coding. What I've just been talking about is noise and reducing its effect, and this is called channel coding. Schemes in A are aimed at trying to maximize compression rates, reducing the number of bits that we have to send. Schemes in channel coding trying to reduce the number of bits we have to add in order to reduce the chances of error. Coding schemes are a very important area of computer science. Now, later in the program, I believe in the module Advanced Algorithmics Comp 309, you may meet schemes such as Huffman coding, live-example coding later on in the program.